Can I start? So today we will be talking about number theory. So these are the basic topics we are going to cover today. Primality test, basically checking a number with whether it is prime or not. Sieve, prime factorization, modular arithmetic, modulo inverse, binary exponentiation, like all are written. Euclidean GCD, NCR, and Euler-Toschen function. So primality test. Like anyone would like to answer how to check whether a number is prime or not? Okay. Yeah. Yeah, that's right. We traverse from 2 to the square root of n, or the brute force approach is to n, and the optimized approach is to square root of n. And we check whether any number divides n. If we found any one number that divides n, that means n is not a prime, else n is prime. So, like 2 to n, we check for 2 to n minus 1. And the proof of that square root of n is like that all factors occurs in pairs, like in form of a comma b, and if a into b is equal to n, one of the a or b has to be less than or equal to square root of n. So if we only check till square root of n, we can determine whether the number is prime or not. Is everyone clear with that, or any doubts? Should I tell, like, with an example? For example, in case of 49, we traverse from 2 to 7, and we get 7 as a divisor, so that's not a prime. And in case of any prime, of course, it won't be divisible. Yeah, so this is the code of the brute force approach. Like if n is 1, then return false. 1 is not a prime because. And else it's going from 2 to n and checking whether it's. Oh, sorry, actually that's reverse code. That's not prime, sorry. So if n mod I is not equal to 0, then return false, else return true. Code ulta ho gaya, sorry. So if we find any factor, then we return false that the number is not prime, and else we return true. I guess code was first. So sorry about that error. So if we want to implement the square root approach, we just do I into I less than n, less than equal to n, and same code goes for it also. Anyone has doubt or? So now the question comes, if we have to find all the prime numbers from 1 to a given number n, how do we do that? Anyone would like to answer? See, yeah, we are gonna discuss that only. Any other approaches yeah, see was the next topic only. So yeah, we can go from 1 to n and check whether each of them is prime or not, but that would take n root n time. Time complexity wise, because for each number we are checking root n, we are doing root n operations for checking whether the number is prime or not. So we don't take that approach. We for bigger n, we take this approach of sieve. So yeah, the traditional approach would take n root n time. So if we want to find whether, like, how many numbers from 1 to n are prime or not, so what we basically do is we mark the composite numbers as false, and initially we assume that all the numbers are true, like all the numbers are prime from 1 to n, and then we keep marking the composite numbers as we find them. So like we will go on multiples of 2 and mark them as composite, then we will go on multiples of 3 and mark them as composite, and then multiples of 4, and so on. So this approach is O n log n, like this is log n. Log n is a different approach. So that takes n log n. If we optimize that further, it would take n log n by implementing the least prime factor or linear sieve. The code लिखने को कुछ नहीं है समझाओगे सर? ठीक है. So ID पे क्या लिखा है स्क्रीनशॉट में? So this is the basic code of implementation of sieve. We go initially we go on each number and assign that as true. Then we go on multiples of those numbers who are prime or multiples of any numbers, and then we assign them as false. So the multiples of 2 like 4, 6, etc. are not prime. We mark them all, and the resulting array basically tells if the ith index is prime or not. Basically the I is prime or not. So koi doubt? Nothing. Sorry. Time complexity of this algorithm, what I have implemented, it's n log n in this case. We can implement it in ON also. I will provide the link later of that approach. Basically, in that approach, we store the least prime factor of each number. And if the least prime factor is same as the number, then we say it's prime, else it's not. So that's an ON approach. I'll like share the link. This wasn't included in this one. I'll include the approach in next class. So there are additional algorithms, like yeah, it's given in additional algorithms. So segmented sieve. Anyone has an idea about segmented sieve? So segmented sieve is in use when we the range is not basically from 1 to n. It's any range, but the difference of range is not very big. Like we want to find whether how many numbers are prime between two numbers a to b, where a to b are in the range of 10 power 15, let's say, but their difference is 1 million or something. So how would we do that? Any ideas on that? No ideas. So what we basically do is we go to the square root of bigger number, and on the multiples of each I, for I is equal to 1 to square root of bigger number, and on multiples of each I, we just mark the array from, like we create an array of numbers from a to b basically, and then on that array we mark the multiples of 2, 3 until square root of b, and we can calculate the multiple of a number in O1, right? What's the just next number divisible by 2 greater than a? We can calculate that in O1, right? So we do that for every number from 1 to square root of b, basically, if you want to find from a to b, and we mark the multiples as false of all those numbers, and the numbers which are left as marked as true, those are prime. So we want to find it in a range from A to B, where A and B are quite large, let's say 10 power 12, 10 power 13 range, but the difference is not very large. Difference is in the range of, let's say, 1 million. So what we do is we create an array of 1 million elements, denoting from the elements from A to B, and A plus ith index ith index stores whether A plus I is prime or not. And what we do is now we iterate from j from 2 to root of b, and on the multiples of j we mark each index false. Like we calculate what's the just next number that is a multiple of j and greater than equal to a, that can be calculated on O1, and now we mark multiples of j, like we just keep on adding j and mark them all of them as false, that it's got divisible by j. Clear? Sorry. Yeah, square root of b is mostly less than a, but from a to b, if the numbers are from a to b, like we use the same approach now. If the number is prime, we will find a factor in 1 to root n. No? So every for every number, we will if the number is not prime, we will find a factor between 1 to root b. So that's why the approach works. Okay, clear? Yeah. So how do we do the prime factorization of a number? Anyway. Yeah, the square root n approach is right. Yeah. Division method, if n is composite, it would have a factor between 1 to root n. So we keep on checking from 1 to root n whether there is a factor or not. And if we find a factor, we keep dividing by that factor till it is divisible. And now if at the end we last with a number greater than 1, then it's the largest prime factor of n. And if we end with 1, then we have just done the prime factorization. So here is an implementation of that. In this code, I have just took the pair of intent, basically the number and the power, and I go from I to 2 to square root n, and I check for every I if n is divisible. Here I declare p equal to 0, that is power, and till n is divisible by I divide n by I and power plus plus, and then in answer I push back power. And in the end, if n is greater than 1, then we are left with the largest prime factor. Like, for example, if n was 2 into 5 into 5 into 7, then we would go on 2, divide it, and then we would go on 5 and divide it. But then at n would be left 7, and I would increment to 6. So 6 into 6 is greater than 7, so it would not go into the loop. So it would come out, and if n is greater than 1, we would end with the largest prime factor of n. Is that clear, or any doubts on that? Like, you can't have a prime factor greater than root n, na? Matlab. 6 into 6 is not a prime, like prime. Like if the largest prime factor has a power greater than 2, अगर largest prime factor power greater than 2 है, then square always I will be less than square root n, and the loop will go on. If the power of largest prime factor is 1, then only we will get greater than 1, no? Clear? So moving on to the next one, binary modular exponentiation. Sorry, upon that, we can if we want to find the prime factorization from numbers from 1 to n, how would we do that? Any ideas on that also? Yeah. Yeah, so we can store largest or the smallest prime factor of each number and through sieve, and we would go keep dividing the by that factor, and once we get one, we are done with it. So this approach is, I guess, also clear. Yeah, so binary modular exponentiation. So let's say we have base and an exponent. We have to find a power b, and b is too big to like just for loop and multiply a b times. So what would we do? And we have to obviously mod something. So what would we do if we want to find a power b mod some number mod, let's say, and b is quite large? Sorry, like a power b mod of mod, let's say mod 10 power 9 plus 7, let's say. Hmm. Hmm. Like b is too big, you can't just loop on b. Like b is of the range 10 power 9, so you can't just go with the for loop. एनी आइडियाज, कोई भी आइडिया आ रहा हो बताओ, शेयर करो. ठीक है. सो बेसिकली कर क्या सकते हैं, जैसे लेट से ए पावर हमें 128 निकालना है, तो क्या अप्रोच हो सकती है. लेट से ए पावर 8 निकालना है, छोटे नंबर्स के लिए लेते हैं, तो क्या अप्रोच फॉलो करेंगे. सॉरी. या ए पावर 4 इंटू ए पावर 4, और ए पावर 4 निकालने के लिए सेम ए पावर 2 इंटू ए पावर 2. सो ये अप्रोच फॉलो करेंगे. तो यहाँ भी सिमिलर अप्रोच फॉलो करते हैं. ए पावर बी को बेसिकली अगर बी इवन हो तो ए पावर बी बाई टू इंटू ए पावर बी बाई टू दो नंबर्स में ब्रेक कर देंगे. और बी अगर ऑड है तो ए पावर बी बाई टू इंटू ए पावर बी बाई टू इंटू है. तो ये रिकर्सिव होता है, मैंने आइटरेटिव लिखा. सो तो बेसिकली ये रिकर्सिव चीज़ थी जो बताई. आइटरेटिव को भी सेम चीज़ में लिख सकते हैं. वी कैन राइट आइटरेटिव ऑल्सो. So linearly multiplying, instead of linearly multiplying, we can convert them into binary, the power. And if the basically the power is odd now, right now, we multiply, we basically store two variables. One is answer and one is base, right? So if answer is odd, sorry, if power is odd right now, we multiply base by answer. Sorry, we multiply answer by base, and we just square the base and divide the power by 2. And else we just square the base and divide power by 2. It's basically the same thing, we are just doing it in an iterative way instead of recursive. So basically if it was a power 17, we just wrote it a power 8, a power a square whole power 8 into a. So we will replace a by a square. First we will multiply a in answer. We will replace a by a square and divide the power by 2. It's clear? So here is a code of that. I have to variables answer, base and exponent. And till exponent is greater than 0, and if exponent is odd right now, what we can do is we can go answer into base, basically what I did right here, a power 17 in case. I did a is answer equal to answer into a. And now I did a equal to a square, like base equal to base square, and then exponent by 2. So exponent now got 8, a got to a square, and answer is a. So that would be left with a into a square power 8, which is right now. So next we move on to modular arithmetic. Like many of you would have seen the symbol A equivalent to B mod M. What does that mean actually? Anyone who knows about modular arithmetic, please? Hmm. Yeah, correct. So if we divide the first number by m and second number by m, then what we get the remainder should be same. Then we write the symbol A equivalent to B mod m. It's basically when we divide A by m, then the remainder we get is same as the remainder when we divide B by m. So there are some properties of modular arithmetic. A plus B mod m, we can simply do A mod m plus B mod m whole mod m. And in case of A minus B, we just have to take care we don't go negative. And so that's why there is a plus m in between. And in multiplication also, it's same as addition. And of course, it can be seen that division would not satisfy this, because like what's the remainder and you are dividing by that. So division doesn't work. For division we use the multiplicative inverse, which we'll talk about right next. So how do we like successfully implement division in modular? Any ideas on that? Yeah. And how do we find B inverse? Yeah, and yeah, that's correct. And that's correct basically. And what in case of non-prime?
Torsion of M.
What? Sorry.
We would use torsion of M.
Yeah, we can use that. Yeah, we can find. Yeah, we can use that also, and or we can find by simply the Euclidean method also. That's like we use for finding the GCD. We'll talk later on that. बहुत दिक्कत हो रही है यार ऐसे बिना समझाने में. अरे कोड तो करा दूंगा, मैथ्स की चीजें ऐसे कैसे समझाऊंगा हमें? टाइप कर लेता हूँ, ठीक है. बैटरी खत्म है उसकी. है Ctrl 3. वो तो ठीक है. बिना माउस के क्या करूँ? ठीक है. हाँ करता हूँ, टाइप करता हूँ. हाँ, रहने देता हूँ. हाँ, तो मल्टीप्लिकेटिव इनवर्स निकालने के लिए हम फॉर्मास थ्योरम को यूज़ करते हैं. तो फॉर्मास थ्योरम बेसिकली, सेकंड यार टेक्स्ट बड़ा कर दो, ठीक है ना? इतना इतना दिख रहा है ना इतना? तो फॉर्मास थ्योरम बेसिकली कहती है कि ए पावर p माइनस वन फॉर इज इक्वल टू वन mod p, yeah, if a and p, yeah. तो फर्मा's लिटिल थ्योरम बेसिकली सेज कि a पावर p माइनस वन इज इक्वल टू वन मॉड p. लाइक a की पावर p माइनस वन को अगर हम p से डिवाइड करेंगे तो रिमाइंडर वन आएगा. अगर मतलब इफ a इज नॉट डिविजिबल बाय p, else जीरो आएगा. सो हम बेसिकली वी यूज दिस टू फाइंड मल्टीप्लिकेटिव इनवर्स. So multiplicative inverse of a number a is defined as a. तो मल्टीप्लिकेटिव इनवर्स को हम ऐसे डिफाइन करते हैं कि किसी भी नंबर a का मल्टीप्लिकेटिव इनवर्स मॉड m में वो होता है जिससे मल्टीप्लाई करने पे a को जिससे मल्टीप्लाई करें तो इक्वल टू रिमाइंडर वन आ जाए. बेसिकली a इंटू बी, इफ वी डिवाइड a इंटू बी बाई m, then the remainder should be 1. That's how we define multiplicative inverse of a. So ये रिलेशन आता है. तो so from Fermat's little theorem and this definition we can find how can we find the multiplicative inverse of a. like we just write a power p minus 1 as a into a power p minus 2. And we know that by Fermat's theorem this is equal to 1, right? So now we can say is a power p minus 2 is multiplicative inverse of a. So this part everyone is able to understand. So, and for calculating a power p minus 2, we just use binary exponentiation method if p is large enough. Many times p is given 10 power 9 plus 7. So we use this relation. It has now, if we can find the modular inverse of a, we can have many uses like calculating NCR and PR. It's quite difficult to divide by r factorial and minus r factorial, but through this we can do it easily. Simply we just power it by p minus 2 and it just becomes inverse of itself. फुल स्क्रीन का शॉर्टकट पता है किसी को? F5 रुक जा, ना ना नहीं है. अरे भाई तू मरवा तू मरवाएगा सही. F11 वो तो ब्राउजर का फुल स्क्रीन होगा ना ये. नहीं छोड़ो. हाँ अरे वो तो ब्राउजर की होती है ना, एक गेस. हाँ ब्राउजर की कैन लॉगिन की. छोड़ो. कहाँ? अरे माउस नहीं चल रहा है, ले जाऊँ कैसे? क्या F एक सेकंड छोड़ो, रहने देते हैं. अबे यार क्या प्रेजेंट एक सेकंड. ठीक है चल. So now we go move on to Euclidean GCD. हाँ पोर्ट नहीं है. हाँ नहीं है. So Euclidean GCD. GCD is basically greatest common divisor, what we studied in classes like HCF also. Many of we. So if we are given two numbers, how would we find the greatest common divisor of them? Hmm?
Factors.
What? Sorry?
Listing down of A and B factors.
Listing down of it.
Listing down of A and B factors. That
Like I
I'm talking
can't
about.
understand. Like
You're
I
talking
can.
about GCD of given.
हिंदी में बोला है. क्या? Factors. ना factors थोड़ा slow हो जाएगा listing. Okay. Like listing down the factors of A and B. हाँ ठीक है कर सकते हैं. But वो square root of A comma B approach I guess होगी. If you implement like you अगर इंक्रीजिंग ऑर्डर में हो फैक्टर्स एंड स्टिल वी अप्लाई 2 पॉइंटर ऑन इट, उसके बाद जाके वो स्क्वायर रूट भी बनेगी, स्क्वायर रूट ऑफ ग्रेटर नंबर. सो दैट्स फाइन, दैट्स करेक्ट, बट थोड़ा स्लो है. सो हाउ डू वी डू इट फास्ट? या माइक लेके बोलो, माइक लेके बोलो.
लाइक हम दो नंबर को ऐसा सब्ट्रैक्ट करेंगे, ऐसा लाइक सॉर्ट करने के बाद उनको फिर स्मॉलेस्ट एलिमेंट जो होगा उससे ट्राई करेंगे डिवाइड करने का. यदि नहीं होता तो फिर से सब्ट्रैक्ट करेंगे उससे उन्हें.
हाँ दैट्स आल्सो करेक्ट, बट सब्ट्रैक्ट करते करते अगेन ऑपरेशंस बहुत ज़्यादा. अप्रोच सिमिलर है, मतलब सेम ही ऑलमोस्ट. बट सब्ट्रैक्ट की जगह मॉड कर देते हैं.
ओके.
हाँ. सो बेसिकली जो लॉन्ग डिवीजन मेथड हम फोर्थ क्लास में पढ़ते थे जीसीडी निकालने का, इफ एनीबॉडी रिमेम्बर्स, तो सेम अप्रोच लगाते हैं अभी. सो इफ लाइक हम क्या करते थे, दो नंबर्स लिस्ट डाउन करते थे लॉन्ग डिवीजन मेथड में, ए एंड बी को ऐसे डिवाइड करते थे. एंड उसके बाद जो रिमाइंडर आता था ए को अंदर रख देते थे, रिमाइंडर को फिर उसकी तरह डिविडेंड की तरह यूज़ करते थे, डिवाइजर की तरह. तो सेम अप्रोच यहाँ भी लगाएंगे. तो या तो जी सी डी ऑफ ए कॉमा बी को हम रिप्लेस ए ग्रेटर देन बी मान लेते हैं अभी. सॉरी, हाँ, ए ग्रेटर देन बी माने तो अब हम जी सी डी ए कॉमा बी को जी सी डी बी कॉमा ए मॉड बी लिख सकते हैं. तो किया भी यही लाइक. सो यूलर ने ये यूलर बेसिकली केम अप विद दिस टेक्निक ऑफ फाइंडिंग जी सी डी. सो हाउ लाइक can anybody tell how the complexity is O log minimum? बोल. हाँ. any ideas कि इतनी जल्दी मतलब log की complexity आ कैसे रही है? हाँ, कम तो हो रहा है बट कम हो रहा है ये तो पता है, बट log कैसे आ रही है, रूट क्यों नहीं है, लाइक मतलब कुछ और क्यों नहीं है? तो डिजिट्स कम थोड़ी ना होते हैं कि हर बार. हाँ, इंट्यूटिव तो है बट कुछ मैथमेटिकल प्रूफ. सो बेसिकली इसका आइडिया वो होता है कि अगर कोई भी एनी नंबर ए है एंड उसको कोई भी छोटा नंबर बी है, बी लेस देन ए है, देन व्हाट इफ वी डू ए मॉड बी. या सो ए मॉड बी इज ऑलवेज लेस देन ए बाय 2. ये ट्रू होगा या नहीं होगा? बिकॉज इफ बी इज ग्रेटर देन इक्वल टू ए बाय 2, तो वो मॉड ए माइनस बी आएगा विच इज लेस देन ए बाय 2. एंड इफ बी लेस देन इक्वल टू ए बाय 2 है, तो वो लेस देन भी आता है मॉड विच इज अगेन लेस देन ए बाय 2. सो वेन एवर वी डू ए मॉड बी, we always get a number less than equal to a by 2. So in हर दो ऑपरेशंस में हम यहाँ मिनिमम को एटलीस्ट हाफ कर रहे हैं. तो दैट्स व्हाई द कॉम्प्लेक्सिटी इज लॉग मिनिमम ए बी. सो मिनिमम ऑफ ए बी इज गेटिंग एटलीस्ट हाफ or lesser in each operation. That's why the complexity is O log. So there are two approaches. This is the recursive approach of GCD. Yes, I guess everybody is clear with that. No, like it wouldn't matter. Like if B is, let's say, greater than A, then we would go B comma A mod B, which is again A. So B comma A is always like this function reverses the order if the order is, अगर order पे initially उल्टा दिया तो ये reverse कर देता automatically. So it would go GCD A comma B, then GCD B comma A, and the order would be maintained from then. So how would you calculate NCR modulo some number given n and r are large enough. Like how would you calculate if let's say n and r both are given less than equal to 1000? Small, like for let's say 1000 n and r are till 1000, how would we calculate NCR? Mod, obviously mod some number. Hmm? Sorry? Modular inverse, yeah, we can use, yeah, that's what I was going to talk about. We can, yeah, modular inverse is of course a better technique, but we can also use the recurrence relation of NCR. That NCR equal to n minus 1 CR plus n minus 1 CR minus 1. So we form a DP like that and we can calculate NCR through that. So ये recurrence relation पता था ना सबको? Clear, ठीक है. So NCR निकालने के लिए what we do is we pre-compute all the factorials from 1 to n, let's say. We have given the range of n. N is, let's say, from 10 power 5 till. So we pre-compute the factorials from 1 to n. And now what we do is we know NCR equal to n factorial by r factorial n minus r factorial. So now what we do is we calculate, we just take the value of n factorial from the array, what we have stored, and we compute the inverse of r factorial and n minus r factorial and multiply it with that. So it can be done faster and it can be done in O1 also. How would we do that? Anyone has idea? Like this is the approach of O log and we go n factorial divided by that. So it can be done in O1 also. तो O1 में कैसे करेंगे, आइडिया बताओ कोई. Like r factorial n minus r factorial log n अच्छा रहता है. तो इसमें log of mod minus 2 बेसिकली लगेगी complexity because binary exponentiation में log of exponent लगती है ना. So log of mod minus 2 it will take. So how to reduce that to 1 or like something? Yeah, we can pre-compute inverse factorials, and how would we do that also? DP में like कैसे inverse factorial को like inverse factorial equal to factorial I power mod minus 2. यही. So wait me tell. So हम last factorial actually निकाल लेते हैं. Let's say 1 to n तक की लिमिट हमने निकाल रखे हैं. We have already calculated the factorials. We just find the inverse factorial of n. And now we do that I into inverse factorial I equal to inverse factorial I minus 1. This relation would, हाँ, so last वाला निकाल लेते हैं और उसके बाद पीछे चलते जाते हैं into I करते हैं. So inverse factorial, we would find the area of inverse factorials and then we can compute easily. So ये है implementation. So compute factorial function just basically computes the factorials. Modulo inverse returns the modulo inverse, of course, power p minus 2. And NCR is just returning factorial n into modulo inverse factorial r into modulo inverse factorial n minus r. So कोई डाउट तो नहीं है ना इस कोड में? कोई डाउट है तो पूछ लो. टिल नाउ अब तक जो पढ़ा है उसमें भी कोई डाउट हो, पीछे का भी कोई टॉपिक ना समझ आया बता दो. So moving on to Euler-Tocient function. So again, if we are given a number n, how would we count the number of integers that are co-prime to n? And anyone please tell कि pace थोड़ा तेज हो रहा है, थोड़ा slow पढ़ाऊँ या normal है? क्या? Normal? ठीक है. So co-primes calculate कैसे करेंगे? कितने numbers co-prime हैं इनसे? There would be like brute force approach तो obviously कर सकते हैं कि GCD निकाल के देखते रहे हर एक का 1 आ रहा है नहीं आ रहा. वो तो कर ही सकते हैं. उसके अलावा क्या कर सकते हैं? Sorry? Yeah. Euler's function. So how we calculate that? Please elaborate. Yeah. 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 So basically, we multiply n by 1 minus 1 by p1 into 1 minus 1 by p2 for every p that divides n. Yeah. Yeah. That's only. And how does that formula occur? Do you know the proof? पता? Yeah. Yeah. Like, but that's correct. But symmetry proof कर सकता? Like जो बचे नंबर्स होंगे वो एग्जैक्टली 1 से n नहीं बचे ना, कुछ एलिमिनेट भी हो गए. तो हाउ वुड यू कि अब भी p2 minus 1 by p2 ही बचेंगे, तो सिमेट्री ब्रेक हो गई ना. लाइक 1 to n में तो सिमेट्री थी कि 1 से n तक सारे नंबर्स हैं तो n by p1 ही होंगे. तो बट जब हमने सारे मल्टीपल्स ऑफ p1 को एलिमिनेट कर दिया तो अब भी वो सिमेट्री होल्ड करेगी, ये प्रूफ कर सकते हो? एक्चुअली करती हो इसलिए क्योंकि सारे प्राइम्स आपस में एक दूसरे के कोप्राइम होते हैं. सो कोप्राइम्स में ये सिमेट्री होल्ड करती है कि कोई भी नंबर से डिवाइड करो तो किसी भी कोप्राइम के मल्टीपल्स पे फ़र्क नहीं पड़ता. छोड़ो. एनीवे, सो बेसिकली इंक्लूजन एक्सक्लूजन से कर सकते हैं. परम्यूटेशन कॉम्बिनेशन में जेई में सबने पढ़ा होगा आई गेस, इंक्लूजन एक्सक्लूजन प्रिंसिपल. सो लिख के दिखा देता हूँ यार. तो इंक्लूजन एक्सक्लूजन में मान लो कोई नंबर n है, वो p1 पावर अल्फा 1 इंटू p2 पावर a2 pm पावर am है. सो तो अब हमें नंबर ऑफ इंटीजर्स निकालना जो n से कोप्राइम है. सो initially we consider that all are coprime. So n minus, we know that the multiples of p1 are not coprime with n. So there are n by p1 multiples of p1, right? है ना? So n by p1. Similarly, we eliminate the multiples of P2, right? So minus n by P2. And we do this, and now we know that the numbers which are multiples of P1 and P2 got eliminated 2 times. In P1 also and P2 also. So that's the that's the basic principle, inclusion exclusion. So we apply that. So this is P I P J. So once from this summation, if we take n in common, then it is like 1 minus 1 by P1. Basically, sigma 1 by Pi minus 1 by plus 1 by Pi pizza minus 1 by Pi pizza P क्या until end. Now we can see that this is basically ये roots में coefficients आते हैं ऐसे taking one at a time, taking two at a time जो दिख रहे हैं. तो किसी भी polynomial के roots में ऐसे coefficients होते हैं ना जो represent करते हैं चीज़ों को. तो through that help we can write this as n into 1 minus 1 by p1 into 1 minus 1 by p2 until 1 minus 1 by pm. Sorry. So yeah, that's how we find the Euler-Totschen function of any number n. So if now we want to find the Euler-Totschen function of from numbers from 1 to n for each number, how would we do that? Hmm? Yeah, correct. Basically, see, yeah. So basically, we will again apply the technique of sieve. If we want to find for all numbers, we will go on each prime, and for each of its multiple, we will let's say the prime is p. So for each of its multiples, we will multiply the initially we will take the Euler-Totschen function of I as I for every number, and once we encounter a prime number p, we will go on its multiples and multiply by p minus 1 by p. And in the end, we will get the Euler-Totschen functions from 1 to n. And through C, we can see that the complexity will be n log n. Yeah, so talking about the complexity of C, has anybody has the proof how the complexity of sieve is n log n? Like, can anybody prove? Hmm. Yeah. So, summation 1 by x less than equal to log x, I guess. पता ही होगा. So summation 1 by x less than equal to log x का proof में we just do one basically in sieve की complexity आएगी n plus n by 2 plus n by 3 plus n by 4 till n by n, right? Now if we take n in common, it will go with like 1 plus 1 by 2 plus 1 by 3 till 1 by n. And we can note that this sum is less than equal to log n, like 2 log n. We can prove that by replacing it with n into 1 by 1 plus 1 by 2. This sum is less than equal to n into 1 plus half plus 1 by 4 times plus 1 by 8 times and so on. So like this will get n into 1 plus 1 plus 1 log n times, right? तो है नहीं मेरे पास. Okay. बता ही देता हूँ यहाँ पे भी. So basically C complexity में 1 plus Let me this 4 times. This 8 times. So we would get like distinct powers of 2 as log n. Log n distinct powers of 2 we will get, right? So, and each power gives a factor of 1. So n into 1 plus 1 log n times. So this would give a complexity of n log n. Any doubts? क्लियर नहीं है तो बता दो, कुछ क्लियर नहीं हुआ तो. और आवाज आ रही है ना पीछे तक मेरी? सुनाई दे रहा? मेर क्लियर? अर्जुन भैया क्लियर? बढ़िया. So, तो यार फिर से पंगा. एक second. Yeah, so there are some properties of Euler-Torschian function now. So as we know, we found the expression for a Euler-Torschian function of n as n into 1 minus 1 by p1 till 1 minus 1 by pm. So now if two numbers n and m are co-prime, so a and b in case like written in slides. So phi ab equal to phi a into phi b. Can anyone tell how if ab are co-prime? Yeah. Yeah, so they would both have different primes, so all of the factors will get multiplied and we will get the same thing. Phi a into b is phi a into phi b for a comma b as co-prime. Yeah, this is the relation and this is the code for computing. So we are going on every number like same which divides and we are multiplying by I minus 1 by I. ये ओ स्क्वायर रूट एन अप्रोच जो शुरुआत में बताई थी वही है. सो डाउट है किसी को इस कोड में? और ये सीव का कोड है. कोई डाउट हो तो बताओ. सो यहाँ पे फाई अरे ले रखी है n+1 साइज की एंड इनिशियली फाई आई इक्वल टू आई हैव डिफाइंड. सो एंड इफ on traversing, if phi I is still equal to I for any I, then we know that I is prime. So on the multiples of I, we just go phi j is equal to phi j minus equal to phi j by I or into equal to I minus 1 by I. So इस कोड में कोई दिक्कत हो तो बताओ, नहीं तो आगे बढ़ो. नहीं है, ठीक है. अब यार सो ये कुछ बेसिक नंबर थ्योरी फंक्शंस हैं जो रेगुलरली काम आते हैं. नोट करना चाहो कर सकते हो. लाइक जीसीडी है बताया था अभी, एंड एक्सपोनेंशिएशन बाय एक्सपोनेंशिएशन. एक्सटेंडेड जीसीडी बेसिकली फंक्शन वो होता है जो 10th क्लास में यूलर्स थ्योरम थी ना एक कि जी सी डी इज इक्वल टू ए एक्स प्लस बी वाई फॉर्म में रिप्रेजेंट हो सकता है हमेशा ए कॉमा बी का, तो वो एक्स और वाई कोफिशिएंट्स निकालने कैसे हैं उसके लिए एक्सटेंडेड जी सी डी यूज होता है। वो 10th में निकालते थे ना कॉपी पेन पे करके, रिमाइंडर लेते रहते थे बार बार, तो सेम काम यहाँ भी है। सी एडिशनल सब्ट्रैक्शन डिवीजन एंड इनवर्स। सो स्लाइड्स में तो भी इतना ही है। एक दो इंटरेस्टिंग प्रॉपर्टीज हैं उसे फाई के बारे में। सो किसी भी नंबर एनी नंबर n कोई दिया हो तो फाई ऑफ आई व्हेन आई इज अ फैक्टर ऑफ n, तो सारे n के सारे फैक्टर्स पे अगर मैं फाई का समेशन करूँ तो n के इक्वल आता। तो ये काफ़ी इंटरेस्टिंग प्रॉपर्टी होती है, कई बार यूज़ हो जाती है, लाइक काफ़ी बार नहीं भी होती है, बट सो मेरी तरफ से इतना ही था आज के लिए। एनीवन हैविंग डाउट्स पूछ लो। सैम्पल एग्जांपल्स थे नहीं आज एक्चुअली मेरे पास, क्योंकि बेसिकली ये मैथ्स ही है, तो अभी कोड में कुछ खास है नहीं, जो लॉजिक है बेसिकली वही कोड कराना है, तो सैम्पल प्रॉब्लम्स थे नहीं आज मेरे पास इतने प्रोवाइड करने के लिए। नेक्स्ट क्लास में कर दूंगा प्रोवाइड इसके लिए। एंड कोई डाउट हो किसी किसी फंक्शन में, कोई भी एक्सप्रेशन जो लिखी हो कॉम्प्लेक्सिटी निकालने में कि कैसे आ रही है क्या। लॉग लॉग एन एक्चुअली वो लॉग एन होती है, लॉग लॉग एन आई डोंट नो क्यों लिखी है, लॉग एन होती है एक्चुअली, वो लॉग लॉग एन नहीं होती, लॉग एन होती है, बाय मिस्टेक लिखती होगा। लॉग लॉग एन एक्चुअली स्मॉलेस्ट प्राइम फैक्टर फाइंड करने के लिए होती है, जब बेसिकली डिवाइड करते जाओ तो प्राइम फैक्टराइजेशन में स्मॉलेस्ट पावर से किसी नंबर n को, बेसिकली किसी नंबर n को अगर बार बार डिवाइड करो तो लॉग लॉग n आती है। लॉग एन होती है, वो लॉग लॉग एन गलती से लिखा होगा, लॉग एन होती है अभी के लिए। एक सेकेंड। तो आज के लिए इतना ही है सेशन। हाँ थैंक यू। और एनी फॉल्ट्स टीचिंग में कोई तो बताओ, क्या इम्प्रूव कर सकते हैं नेक्स्ट टाइम से। हाँ वाइट बोर्ड हाँ लगाना है। और कोई इम्प्रूवमेंट्स।
So, any suggestions for Nishkarsh and the way he taught? Bhavishya? Abhinav? All right then. Uh, we'll conclude the session then, and I would request you all to join the Discord server if you haven't, and you can ask your queries there. I hope you are practicing the problems, and tomorrow's session will be held at the same venue, that is here at 11 a.m. and we'd expect you to come. And other than that, a round of applause for Nishkarsh. And I hope he improves and keeps teaching you a lot of new things. And another thing that I would like to add is that this week there are 2 sessions, although in the upcoming weeks we'll have one. This one is to accommodate the class which will not happen due to your midsems. All right. So during your midsems we'll skip one class, and this class was to accommodate that class. And finally, thank you everyone, and I hope